Hi and welcome back everyone. In this video we're going to continue on with AC circuits and specifically look at how we can measure an AC circuit. Somewhat more complex than a DC circuit, so let's begin. First thing, let's just go back and review some things about AC circuits and why do we use AC circuits. So remember that alternating current or AC power is the most common form of electric power produced in North America and in the rest of the world. AC power is used in our homes to power devices like ovens, refrigerators, and air conditioning units. Understanding AC power and AC circuits is important for many fields of engineering and other disciplines. It's a number of common AC waveforms that we can examine. We can look at square waves, triangular waves, sine waves. Out of these three, the most common is the sine wave. Typically, a hydroelectric plant is constructed with machines that produce a sine wave for distribution to homes and businesses. Let's focus on the most common AC waveform, which is the sine wave. Here's a typical sine wave and how it is displayed on an oscilloscope. A sine wave, just like an ocean wave, has an amplitude, which is how high or low the wave goes in the direction of the vertical axis or y-axis. As we have this part of the cycle here, this represents the forward movement of current in the circuit, and the bottom half represents the movement of current in the opposite of direction. So in an AC circuit, current is moving in the forward direction, then it's moving in the reverse direction, then it moves in the forward direction, the reverse direction, and continues like that. On the horizontal axis, we can display the sine wave labeled with degrees or radians. If we do, one cycle looks as follows. And we can see that the voltage at 0 degrees, 180 degrees, and 360 degrees is 0 volts. At 90 degrees, it reaches its maximum positive voltage. And at 270 degrees, it reaches its maximum negative voltage. The frequency of the sine wave is how many times the cycle repeats in 1 second. The unit for frequency is hertz, which is really the number of cycles per second. The frequency of the sine wave is inversely proportional to the period and is represented by the letter F. Let's take a look at measuring AC power and how we can do that. Not all sine waves have the same properties. Sine waves can differ in frequency or amplitude. When it comes to the amplitude, we can measure an AC signal using a number of different methods. Let's take a look at some of these. The peak-to-peak voltage is measured from the maximum peak positive voltage to the maximum peak negative voltage. So we can see here that the maximum peak positive voltage is 2.5 volts. The maximum peak negative voltage is minus 2.5 volts. That makes the peak-to-peak voltage equal to 5 volts and is represented by V with subscript PP for peak-to-peak. The AC signal below, as mentioned, has a peak-to-peak voltage of 5 volts. The peak voltage is measured from the maximum peak positive voltage to the horizontal axis, or 0 volts. The AC signal below has a peak voltage of 2.5 volts. It's written typically as V subscript P or V subscript PK. Another way to measure AC power is to use something called root mean square voltage, or RMS. What is root mean square voltage? Well, we need to examine a couple of things before we fully understand RMS. Let's take a look at a couple of circuits. First thing, we have to remember some schematic symbols because we're going to take a look at a couple of schematics here. This is the symbol for a DC source, and this is the symbol for an AC source. Recall that in AC power, the voltage reaches the maximum positive peak voltage and the maximum negative peak voltage at one short instant in time. Voltage is always changing in an AC circuit. If it's not its maximum value, it's obviously going to be less than that. If we have the following circuits, using Ohm's law, the current in the DC circuit will be 50 amps continuously. We've got a 100-volt DC source here. We've got a resistance of 2 ohms. So we know from Ohm's law the current will be 50 amps continuous. However, the current in this circuit, the AC circuit, will only be at 50 amps at the peak voltage. Otherwise, it will be less than 50 amps. Using a formula for power, P is equal to voltage over resistance squared, we can see that the power output for the DC circuit is greater than the power output for the AC circuit because the DC voltage is constant at 100 volts, where it's not for the AC circuit. So is there a way to have a measurement in AC that would give an equivalent power output to the DC circuit output? Yes, and we can do this using the root mean square voltage. So the power output by the DC circuit is equivalent to the power output of the AC circuit if we are using the root mean square voltage. So if we calculate P1 here using the RMS voltage in this AC circuit, compare it to the power P2 in this DC circuit, these powers are equal in watts because we are using the RMS voltage for calculating P1. So how do you derive the root mean square voltage? Let's take a look using a 10 volt peak 50 hertz AC signal as shown below. What we're going to do is we're going to use a circuit analysis tool. We've done a screen capture here, and what I've done is I've measured the voltage at various points in the cycle. So if we let this animation run, you're going to see what I've done here. I've used this circuit analysis tool, and with this 10 volt peak, I'm going to look at the first half of the cycle, and I'm going to divide that up into 10 parts, and I'm going to find the voltage at each of those points. And then what we're going to do is record these values, and then we're going to do some calculations with them. So that's all I'm doing here in this animation. You can see the voltage at various points. It starts at 0 volts and goes up to a maximum of 10 volts. And then it returns back to 0 volts in the first half of the cycle. And what I've done is I've taken those values and I've put them in a spreadsheet. Here we have the time in milliseconds, and here we have the corresponding voltage at various points. So here's the voltage at 1 millisecond, here's the voltage at 2 milliseconds, 3 milliseconds, and so on, all the way up to 10 milliseconds, which is the first half of the cycle. Then in the next column, what I did was I squared the voltage. So I just took this value here and squared it, took this value here and squared it, and completed that for the rest. What I've done in the next column is I've found the mean, which is the average. So I've added these up and I've divided by the number of numbers that I have here to get the mean. And I get a mean of 50.000. And what I'm going to do is I'm going to find the square root. And when I find the square root, I get 7.071. So what we had was an input, which was a 10 volt peak AC signal. And what I get for an output is 7.071 volts. By doing all of these calculations, what I'm finding is the RMS value for this. It turned out to be this here. So the factor between these two is this here. If I took this number 10 and I multiply by this factor, I get this voltage. So for a 10 volt peak AC signal, it really produces an RMS voltage of 7.071 volts. If I repeated the same activity for a 100 volt peak AC signal, I just wanted to show you that if these are the voltages at various points and we square those, we find the mean and we take the square root. For a 100 volt peak AC signal, we get a RMS voltage of 70.71. And what happens is the factor ends up being the same. So regardless of the size of the amplitude, the factor stays the same. So what we're showing is, yes, there's a relationship between the peak voltage and the RMS voltage. And it's given in this formula here. The RMS voltage is equal to 0.7071 times the peak voltage. That's how we can determine the RMS voltage. Another way to do it is using this here. 1 over the square root of 2 is equivalent to this here. You can use either one in your calculations. You'll end up with the same answer. So what this shows is, again, if we have a 10 volt peak AC signal, its equivalent RMS voltage is 7.071 volts. Most of you have probably used a multimeter to measure DC voltage, but what about AC voltage? That is represented by this symbol right here. Here's our symbol for DC voltage, and when we want to measure voltage in a DC circuit, this is measuring AC voltage. Well, first, if we want to measure AC voltage, we need to select AC voltage on the dial, as we've shown here to the right. And second, you need to understand that your voltmeter will display the RMS voltage of your AC signal. So it doesn't give you the peak value or the peak-to-peak value. What we see in the digital output of the multimeter is the RMS voltage. Let's take a look at some examples of RMS voltage. If we have a sine wave and it has a peak-to-peak voltage of 400 volts, what is the RMS value? Well, 400 volts peak to peak is equal to 200 volts peak. And if we want to find the RMS voltage, we just take our factor, which is 0.7071, and we times it by the peak voltage. So in this case here, that's times by 200 volts. and we get an RMS voltage equal to 141.4 volts. So 400 volts peak to peak is equal to 141.4 volts RMS. Let's take a look at another one. An AC voltage has a value of 150 volts RMS. What's the peak value of the voltage? So if the RMS voltage is equal to 0.7071 times the peak, or we could say that the peak voltage is equal to the RMS voltage divided by our factor, then in our example here, the peak voltage is equal to 150 volts divided by 0.7071, and we get a peak voltage of 212.1 volts. So 150 volts RMS is equal to 212.1 volts peak. So how does this relate to Ohm's law and Joules law? Well, most of you have worked with Ohm's law and Joules law with DC circuits, but what about AC circuits? Ohm's law applies for DC circuits and AC circuits. So for example, V is equal to IR. We've done calculations with that for DC circuits. V peak to peak is equal to the current peak to peak times the resistance for AC circuits. Or we could say the voltage in RMS is equal to the current in RMS multiplied by the resistance for AC circuits. So Ohm's law applies to DC circuits and AC circuits. Joules law applies to DC circuits and AC circuits as well. For example, we have done calculations using power. Power is equal to current times voltage for DC circuits, but we could also use it for AC circuits. The peak power is equal to the peak current times the peak voltage for an AC circuit. So let's just quickly review. Sine waves are one type of AC signal, and its voltage can be measured in a number of ways, including peak to peak, peak voltage, and RMS voltage. The power output by the DC circuit is equivalent to the power output of the AC circuit using the root mean square voltage. Ohm's law and Joules law applies to DC and AC circuits. And we can see that in these various forms of it here. So that's it for this video. Hopefully you've learned more about how you can measure AC waveforms. That's it for this video. Thanks for watching, and see you next time.